Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be covering one of the iconic problems of thermodynamics, the Carnot cycle. So here what we're really going to be doing is looking at how we can evaluate the favorability and even efficiency of a system. And this is a classic way that we can do this is by looking at what is called a perfectly efficient heat engine. So a heat engine is the idea of I'm taking energy from a hot source, letting some of that heat go to a cold sink. So again, hot object like a furnace, cold sink, which could literally be cold water or the outside. And I'm going to capture some of this energy as work. Now, it's worth noting you can adapt this same process and make a heat pump by instead putting work in and making the whole process move backwards. And so this has become very popular area of study with heat pumps being a more efficient way to heat a system. Now, this perfectly efficient heat engine, however, is known as a Carnot heat engine. Now, so a Carnot heat engine is going to be the most perfectly efficient heat engine. So it's not frequently made, but it more sets the ideal. Though there is indeed real examples of how you can put one of these together. And again, it's going to work by letting energy flow from a hot source, like a furnace, to any sort of cold sink. And we're going to mostly capture this work as PV work. And this will help tell us what the maximum energy that can be used for work. So what percentage of this heat that I'm pulling off can I turn into something usable? As a hint, entropy says it's not going to be 100%. So we can do this by looking at how a heat engine can work as a series of four reversible steps. And this idea that they're going to be reversible means that this whole process is going to be slow, but also means it's going to be very efficient. And you can make it irreversible to make the system go faster, but will inherently be less efficient. So let's look at this extreme case. So in the reversible case, the first step is I'm going to go ahead and start with more or less an empty piston. And I'm going to go ahead and let energy flow into it by putting it next to a hot source. So this can be something as simple as hot water, it can be steam, it can be a furnace. Now, when I do this, what we're going to see is that piston will naturally expand as the energy flows in and work flows out. But notice it's the fact that it's isothermal, which means the heat flowing in will be exactly equal and opposite to the work going out. So that's going to be very nice. Then what we can do at this point is we can remove the piston away from this heat source and we're going to insulate it. And once this piston is insulated, it is now adiabatic. But what can happen is I can go ahead and slowly and reversibly lower the pressure on this piston, allowing it to expand even further, doing a little bit more work. But the problem is the work from this process has to come from somewhere, and it will come from cooling the system down. So again, we're starting hot this whole time, and now we're going from hot to cold, but getting a little bit of extra expansion, trying to milk that last bit of energy out. Now we've got a very big and very cold piston. So what we can do is now I need to put energy back into it so I can repeat the process. So in the first bit, I'm going to go ahead and put it next to my cold sink, and I'm going to go ahead and actually compress it. So heat will be flowing out into the cold sink, but I'm putting work in. And so I'm going to do this until it essentially hits some uh, uh, till it hits some steady value. And then I'm going to go, it gets to the right temperature. And now I'm going to go ahead and pull away the heat sink, but keep putting extra work in. And now, since it's now insulated, any work that comes in is going to heat the system up because I'm now in an adiabatic compression. And I'm going to do this until I get to my final temperature. So note, we've now completed a cycle. We end at the same place we start. So again, we expand using a hot source. Then we expand further until the system is cold. Then we compress and then compress a little bit more, heating the system up. So again, break it into these four steps that we can know how to examine in detail. And because each of these steps is reversible, that means it's going to be fairly easy to determine the entropy because the entropy is defined based on reversible processes. And this will let us figure out the efficiency of a process. Now let's take a moment and really think about what this looks like more kind of pictorially. So again, the first step, I've got a hot reservoir, heat flows in, we get work out. Then in the second step, we now insulate the system and we're just let it go ahead and get a little bit more work by slowly lowering that external pressure so it expands even further. Now it should be fully cold. So now I can go ahead and compress the system and let the heat flow back out. So again, this work and this heat should be equal. And then I can go ahead and put a little bit more force, heating the system back up to its original temperature. Now let's go ahead and look at what the entropy is for each of these terms. Now, for stage one, this is an isothermal compression, but it's a reversible one. So the change in entropy is going to be simply related to the amount of heat, because this is reversible heat, over the temperature. And because this is isothermal, we don't have to do the integral. It's simply going to be the ratio of that heat to that temperature. Now, for stage two, this is an adiabatic expansion. But adiabatic means there's no heat transfer. And if there's no heat transfer, it means there's no change in entropy. Yes, we get an easy one. Now, one of the important things to remember is the idea of an adiabatic or an isothermal expansion should be very similar to an isothermal compression. And again, since both of these are reversible, hey, congratulations. The hot and the cold, the form should be similar. I'm just replacing the hot heat with the cold heat and the hot temperature with the cold temperature. So now we can go ahead and compress again until we get to the adiabatic compression. But since it's adiabatic, there's also no change in the entropy. That means that when I'm trying to add together all four of these entropies, I get to ignore the adiabatic terms, and that's really easy. But also note, we begin and end in the same place. And so since entropy is a state function, it means the total change in entropy for the system, not for the surroundings, should be zero. So I can just simply add together the isothermal expansion with the isothermal compression. And so that means that these two terms should be equal and opposite. So the ratio of the heat and temp should be the same magnitude, but the opposite sign of the cold heat and cold temp. Now we can also rewrite this to go ahead and get the ratio of the heats to each other and compare that to the temps. Now, when we do this, there's a very important thing that ends up happening. We want to go ahead and ignore the sign. So we're going to just look at the magnitude of the cold heat and the cold temp will be the same as the magnitude as the ratio of the two temperatures. So that means that I can replace any ratio of heat with the ratio of temp. And that's going to come in handy in just a second. So now let's go ahead and use this relationship in between the heats and the temps to evaluate the efficiency of a cycle. So again, because the Carnot cycle is reversible at every step, it will be by definition very slow, but very efficient. So this will represent the maximum efficiency I can get out of any system. Any real system will be faster, but with a lower efficiency. Now we can define the efficiency for any sort of heat engine as the ratio of the amount of work I get out of the system versus the amount of heat I have to put into it. So again, ideal world, this would be 1, but remember our second law of thermodynamics says I can't turn all my heat into work. Some of it's gonna have to leave into the surroundings. Now we can define our net work. So again, the amount of work I get out of the system, ignoring any work I had to put in, is simply going to be related to that difference in heats. So again, it's going to be how much heat I put into the system, how much heat I got out. Anything that didn't leave as heat left as work. So we still have more or less work over heat. Now what we can do is distribute the denominator. And when we do this, well, we have uh, the heat going in over the heat going in minus the heat going out over the heat going in. And we can rewrite this as 1 minus that ratio of heats. But hey, we just said that that ratio of heats is going to be the same as the ratio of temperatures. That means I can evaluate the efficiency of the maximum efficiency of any heat engine as simply being 1 minus that ratio of temps. What that means is if I have a very big temperature difference, so let's say I'm taking energy from the sun and putting it into, say, space, that temperature difference is going to be really big. And that means that this value will be very close to zero, meaning that efficiency will be very close to one. So a big temperature difference will get you a very efficient heat engine. But on the flip side, that also means that the closer my heat sink and heat source are to each other in temperatures, that means the process is going to be a little less efficient. This is also one of the reasons why you can get usually better efficiencies on industrial scale heat engines than you can on more commercial or private because they're going to be smaller and that temperature difference tends to be a little closer and naturally a little less efficient. But in practice, most of these heat engines are often a lot less efficient than you'd expect because don't forget that temperature ratio is going to be in Kelvin. And in that scale, even if I'm going, say, from steam 100 degrees to room temperature 25, 75 over 300, just over 400, just isn't a big difference. So that's really going to limit efficiencies of engines. So next time, we're going to really dive into how we can calculate the entropy more accurately for each of these types of transformations. Until then, take care.